Assalamu alaikum. So I think we're going to have two more lectures, including this one on this quantum information stuff, and then we're going to move on to more physical quantum physics. We're going to look at an equation of motion for quantum physics. What is the analog, for example, of Newton's equation of motion that's used in classical physics? How does it map over into quantum physics? Anyway, today we're going to look at something really interesting. We've already introduced the idea of quantum circuits and quantum networks and quantum logic gates. So we're trying to build this idea a little bit further. We've talked about unitary operators. We've talked about how unitary operators transform quantum states, and so on and so forth. We've also come up with the vectorial representation of quantum states and operators. So all of this is looking really good so far. So let's start looking at a few applications. First of all, I would like to introduce some 2-qubit gates. For example, let me start off with an example. We already know that we have a NOT gate which takes an input and inverts the input. So ket 0 goes to ket 1, ket 1 goes to ket 0. And if you were to write a unitary operator for this NOT gate, this is what it looks like, and so on and so forth. Now this is a single qubit gate. For example, we could have 2 qubits, 2 photons, and we look at the path of each photon, or a photon and we look at the path as well as the polarization of a photon. We could have 2 proton spins, 2 electron spins, and so on. Whatever the physical scenario is, we really don't care about it at the moment, but we have 2 qubits coming in. We could apply a NOT gate on each qubit. So if this input state here, which is now a composite quantum system because it has 2 qubits, if this input state were such that this is ket 0 and this is ket 1, we could write this composite state as ket 0 tensored with ket 1, or simply ket 0, 1. And when this joint quantum state sees the 2 single qubit quantum gates, something else emerges, and what emerges is that the first qubit is inverted and the second qubit is also inverted. So a new quantum state is created in which the first qubit changes from 0 to 1, the second qubit changes from 1 to 0. So ket 1 emerges here and ket 0 emerges here. Now we also know that we can write this quantum state ket 0, ket 1 in terms of a 4x1 column vector, and this is 1 0 tensored with 0 1, and this gives a 0 1 0 0. So this is the input state. All right, and what emerges as the output state is ket 1. So this output quantum state can be written as ket 1 tensored with ket 0. Ket 1, as we know, is 0 1 tensored with 1 0. This would become 0 0 1 0. So starting from a 4-dimensional input quantum state, you achieve another 4-dimensional output quantum state. So there has to be a matrix for this operation. Now this is going to be a big matrix, a 4x4 matrix that converts this column vector to another column vector which has 4 rows. So you need a bigger matrix for that. And what you could do is you can just take, how do you construct such a matrix? You just take the unitary operator matrix for this operation, the matrix for this operation, and form the tensor product. For example, if this is a joint NOT gate acting individually on the 2 qubits, you could form UN1, UN2, a NOT gate on each qubit as the tensor product between the unitary operator for 1 qubit with the matrix for the other qubit. All right, so now we can do a tensor product, which really means you take the first element here and multiply it with all the 4 elements in the second qubit. So you divide this matrix into 4 blocks. The first block is 0 element wise multiplied with each of the 4 elements in the second matrix. So 0 multiplied with all of this gives us 0, 1 multiplied with all of this gives us this, this gives us this, and this gives us this. So overall, this is our unitary matrix for the 2 NOT gates acting individually on each qubit. All right. So now in this example that I've presented, the first qubit is independent from the second qubit. There's really no correlation. So one person might want to just see the first qubit and he wouldn't care about what happens to the second qubit, because these are 2 independent qubits. They are not talking to one another. There's no crosstalk between the qubits. All right. Each qubit is independent. It's just looking at 2 single qubits one by one independently. There's no correlation. However, we can have interesting quantum gates in which the output of one or the operation on one qubit depends upon the state of the other qubit. Now, have you come across logic gates in your A levels? You might have seen, say, are you familiar with, say, I would just call this an AND gate, right? Is this an AND gate? All right. So let's figure out what an AND gate is. So this is an AND gate. So what an AND gate is, I can write a truth table for an AND gate. So there are 2 inputs A, B, and there is one output, say X. So if A and B both are 0, the output is 0, 0, 1, 0, 1, 0, 0. And if both the inputs are 1, the output is 1. So the output depends upon both inputs at the same time. All right. Now this is a logic gate. Everyone is familiar with AND gates, correct? Does anyone not know what an AND gate is? All right. So an AND gate or any gate takes in certain inputs and gives you an output. For example, this is a NOT gate. Do you now by now know what a NOT gate is? A NOT gate takes 0 and churns out a 1, takes 1, churns out a 0. An AND gate in classical physics is a gate, is an operation that takes 2 inputs and gives out 1 output. And it follows a certain truth table. It takes the AND operation of these inputs. AND operation means that the output is high or 1 only if both the inputs are high. So if both the inputs are 0, the output is 0. If only one of the inputs is 1, the output is still 0. But if both the inputs are 1, the output turns out to be 1. So this is how we define an AND gate. There are other kinds of gates as well. For example, you can have an OR gate. A, B, X. And if I were to write the truth table for an OR gate, X, A, B, an OR gate outputs a 1 if either of the inputs is 1. If both the inputs are 0, the output is 0. But if either of the inputs is 1, it outputs a 1. Of course, if both the inputs are 1, it still outputs a 1. This is an OR gate. So all of these gates have certain truth tables, certain definitions. All right. So this is what we mean by a gate. You have certain inputs coming in and you produce an output. In a quantum gate, you have a quantum state coming in and it produces a quantum state as an output. All right. Now, by the way, one question I would like to ask you, now we are at it, is this gate reversible? Is it reversible? Reversible means that if you know the output, can you infer what the inputs could have been? No, it's not. The first problem is that there is only one output. From one output, it's hard to tell both what the inputs are. Only in certain cases can you infer this information. Yes, please?
So I was just saying that if the output is 1, then we can infer that both inputs will be.
Right, but only in one specific case. Only in 1 out of the 4 cases can you do that. So it's not a reversible gate. Quantum gates are reversible. If you knew the output here, you would be able to tell what the input is. Right? So that's one of the power of quantum physics, is that the gates that you make, they are reversible. And reversible operations do not dissipate energy. They do not create heat. So you do not have heat dissipation in quantum circuits of the same kind that you would have in these classical gates, because in these classical gates you are losing out some information. When you lose out information, there are laws of physics that tell you that you have to create some heat. If you lose one bit of information, you kind of create some energy which is lost to the environment. Anyway, this is besides the point. So this is a 2-qubit gate, but this 2-qubit gate is really composed of 2 1-qubit gates. We can have genuine 2-qubit gates as well. What does a genuine 2-qubit gate mean? Let me give you an example. So I'm going to talk about a genuine 2-qubit gate. Let's resort to our circuit model. We have an input qubit and another input qubit, and I draw a gate in this fashion. Let's call this gate a controlled NOT gate. Now, what a controlled NOT gate does, we can of course construct a truth table for it. All right. So let me write down the truth table for this quantum gate. First of all, it's a genuine 2-qubit gate. There is some kind of linkage between the 2 qubits, which is depicted by this line, which starts off at the first qubit and ends on the second qubit. So a NOT gate is applied to the second qubit depending upon what the state is in the first qubit. If the first qubit is in a state ket 0, nothing happens to the second qubit. However, if the first qubit is in a state 1, the second qubit is inverted. It sees a NOT gate. That's what a controlled NOT gate is. You're applying a NOT gate on the second qubit, but it's controlled by the state of the first qubit. All right. So let's draw a truth table for this. The truth tables now, of course, are going to be in a quantum language. So if the input is ket 0, first qubit, second qubit, and I'm dropping off the tensor product sign. I know it exists, all right, but I don't want to write it over and over again. So if I apply the controlled NOT gate, which I give this symbol U, the hat on top of it, C naught, if the first qubit is in a state ket 0, nothing happens to the second qubit. So I'm left off with ket 0, ket 0, ket 0, ket 1 goes to ket 0, ket 1, ket 1, ket 0, however, changes. Can you predict what the output is going to be now? Ket 1, ket 1. What about ket 1? Ket 1, what does this change to? So this is the truth table for a control NOT gate. And by looking now at the outputs, you can infer with certainty what the input would have been. Yes, please?
Sir, I didn't get this part. part. So the NOT gate is controlling the output, like in the first wire.
The first gate, the first wire, the first quantum state is controlling whether you want to apply a NOT gate on the second qubit or not.
How is it turning on?
What do you mean, how is it doing that?
Is it like sending like uska qubit towards the NOT gate, or like if it's one, so the other qubit passes or something?
We're not talking about the physical implementation of these gates for the time being. How do we do this in the laboratory? We're not discussing that. So this is trying to build up a quantum circuit. These gates exist, they can be implemented in the laboratory. You need to know a bit more to understand how to implement it, but it's a valid quantum gate, isn't it?
So to add on to it, can you explain how we got these outputs? Okay, it's the input is 0, 0, so it gets 0. If it's 0, 1, so the only case it changes is like the second output.
And the last one. So if, excuse me, there's a question I'm trying to answer. If the first qubit is in a state ket 1, the second qubit gets inverted. That's what it does. This is how we define this control NOT gate. So the valve, the switch is the first qubit. The state of the first qubit determines what's going to happen to the second qubit. If the first qubit is in a state ket 1, the second qubit sees a NOT gate, otherwise it sees nothing. All right. And by looking at these outputs, there is a one-to-one mapping between the outputs and the inputs, so it's a reversible quantum gate. Yes, please.
So can you explain all of this again?
Come on.
Yeah, please.
Can anyone explain this to students in a possibly a different language? All right. Okay. Let me try. So every gate has a logic table, as a truth table. A controlled NOT gate is also a valid gate. How do we define this gate? We define this gate in the following fashion. This is the truth table for this particular gate that I've drawn in blue. What does it do? It looks at the state of the first qubit, and depending upon the state of the first qubit decides to apply a NOT gate to the second qubit. If the first qubit is in a state ket 0, which is this case and this case, it does nothing to the second qubit, so just the second qubit just remains preserved. However, if the first qubit is in a state ket 1, the second qubit is inverted. In all of these cases, nothing happens to the first qubit. The first qubit just passes preserved, unscathed through this wire. However, the second qubit can see a NOT gate, and that can is determined by what's the state of the first qubit. Do you get this? There was another question over here. Yes, please.
हम लोगों ने assume कर लिया कि अगर वो first qubit ket 0 के अंदर होगा, सिर्फ तभी जो है वो no change होगी. हम ये assume कर सकते हैं कि शायद वो 1 में हो और no change हो और 0
बिल्कुल
में हो तो change हो.
बिल्कुल आप ऐसा गेट भी बना सकते हैं कि in which it inverts the second qubit based upon what the whether the first qubit is in a state ket 0 or 1. If it's in ket 0, it inverts the second qubit. This is a homework problem, Salman. So what I would like you to do right now in class, can you write the 4x4 matrix for such a gate? It's going to be very easy, by the way. You know what the prescription for each of the 4. So these are the 4 basis states, aren't they, for 2 qubits? And these are the 4 basis states for the 2 qubits as well. So it's very easy to write a 4x4 matrix, which of course is going to have 4 columns, which represents this gate. Can you please attempt writing down this matrix which corresponds to this logic gate? The question is, every operation has a matrix representation. I would like to write down the matrix representation for this operation. What's the matrix for this control NOT gate?
Sir, can I ask a question?
Yes.
Sir, in the 4x4 matrix you've drawn above, so what is each section representing? Like the section with all zeros and like Is there a certain way to interpret it?
The selection with?
The section with all zeros, like the top left one. Is there a certain way to interpret it?
So this is the matrix. This matrix acts on a certain input and it gives you the corresponding output. So by looking at this matrix, you can tell what happens to certain inputs. Right? Salman, we need a drill with these matrices and their operations on states in the homework. Each column represents the output when you feed in one of the 4 basis states. When you feed in the first basis state, the output would be written in the first column. When you feed in the second basis state, the output would be written in the second column.
अब हम जो टेंसर प्रोडक्ट ले रहे हैं ये हमारी सुपरपोजिशन है
क्या चीज़?
जो हम टेंसर प्रोडक्ट जैसे हमने लिया था
नहीं, अभी सुपरपोजिशन कोई भी नहीं है।
ये बस 2 साल
ये सुपरपोजिशन नहीं है ना, इत्तेफाक से सुपरपोजिशन हो भी सकती है।
सर ये पूछना था कि हम लेते कैसे टेंसर प्रोडक्ट समझ नहीं
पहले 0 को मल्टीप्लाई करो इन चारों टर्म से, 0 को सीखिए 0 0 0 0 टॉप ब्लॉक आ गया, फिर 1 को मल्टीप्लाई करो इन चारों से तो इधर वाला ब्लॉक आ जाएगा, फिर 1 को करो ये बॉटम लेफ्ट ब्लॉक आ जाएगा।
अच्छा ये ब्लॉक है?
हाँ ये ब्लॉक है ना।
ब्लॉक इससे इससे इससे
पहले इस एलिमेंट को पूरे मैट्रिक्स से करो, टॉप ब्लॉक आ जाएगा।
1 2 3 4
ये पहले 4 टर्म्स आ जाएंगे, 1 2 3 4, फिर इसको करो तो अगली 4 टर्म्स आ जाएंगे।
अच्छा ठीक है।
Has anyone been able to write down the matrix? You can't have 2 1s in a column. आपने लिख लिया? दिखाएं जरा दूर से। So what's your first column? What's the second column? 0 1. Second column, third column, 3 zeros and 1. Good. So this is the matrix. So you look at the first input state. This is the first basis state. The output is just the input state. Ket 0 crossed with ket 0 is a column vector which has 1 at the top position and zeros all the way. This is the second column. The second column has 1 at the second position, all the rest are zeros. The third column, however, is ket 1 crossed with ket 1. And you would like to write a column vector for this. If you want to do it explicitly, this term is 0 1 crossed with 0 1, which is 0 multiplied with both of these terms 0, 1 multiplied with these terms 1. So 1 falls off at the bottom. So now this is the unitary operator, the matrix for a control NOT gate. Now you can feed this matrix with any input whatsoever. You could feed it in with a superposition, for example, any input whatsoever. You just need to write down the vector for the input state and you will get the output vector. The input vector could be arbitrary. It could be a superposition, it could be a basis state, it could be a really complicated state. In all cases, the control NOT gate can be represented by this matrix. Yes, please. क्या मतलब? ये हमने आउटपुट को देख के लिखा है, but in a particular order. The order is the order that you choose to write the basis in. Yes, please. Well, you have to define your order at the beginning. We defined it in our previous class. We have to define it. Yes, please. Because, excuse me, here we took the tensor product for two NOT gates. We can't do this here because now there's a correlation between the two qubits. The tensor product keeps the two spaces distinct and independent and uncorrelated. All right? So this is an example of a genuine two qubit gate. Yes, please?
Could you show an example of how we could use this matrix?
How?
To how we could use this matrix to interpret the output?
All right. So, example. Suppose I have a controlled NOT gate, and this example is out of a desire of a student. You feed in a certain input quantum state. Yaar baatein na karo yaar. Suppose that input quantum state psi in, just for the sake of it, let's suppose this is some state of this kind, ket 0 crossed with ket 0 minus ket 1 over under root 2. This is my input quantum state. Now the first qubit is in ket 0, the second qubit happens to be in a superposition, and I feed in this 2 qubit state into the control NOT gate. Now there are two ways of finding out the output. One is by explicit mental logic. So you can expand the input quantum state as 1 over under root 2, 0, 0, minus 0, 1. This is your input. Now the controlled NOT gate acts on this input state to generate an output state. Output state comes out here. Right? So let's see what the output state is. Nothing happens to the scalars. Now just apply the truth table to this gate, input gate. The first qubit, if it's in state ket 0, nothing happens to the second qubit. Ket 0, minus ket 0, ket 1. Nothing is going to happen to the second qubit because the first qubit in each of these cases is 0. So this is going to be my output. All right. Now I can do this in matrix form as well. What I could do, I could write down the matrix for the control NOT gate, which I've already written down over on the previous side of the blackboard. And now I need to write down what the input state looks like. Now this is a column vector. What's the input? It's this quantum state. So I write down the vector form of this quantum state. It's going to be a 4 by 1 column vector. I write 1 over under root 2 over here, and I just write the representation of this state in the Zeeman basis, which is what? How do I populate the elements of this vector? 1, 3 zeros. So this is just this term. What about this term? This would also give you a 1 somewhere in the column vector. Minus 1 because of this minus sign. This will be my output state. So I do a multiplication of this matrix with this input column vector. I get 1, minus 1, 0, 0. This is just a representation of this quantum state. So actually nothing happens here. The input is the same as the output because I started off with the ket 0 here. The NOT gate isn't really applied. So if I started off with a 1 here, then the output state will be different from the input state. So this is how we use matrices. If you want to use matrices, we write everything in vectorial form. It's not necessary to use matrices, but when sometimes you would like to encode this on a computer or you would do a double check of your calculation, matrices come out really nice. Yes, please. क्या मतलब क्या किया? यहाँ पे देखिए, this is going to be really, really long. So this is an input quantum state. So I want to write the matrix for this or the vector for this. How do I write a vector for a state if I have 2 qubits? 4x4 मैट्रिक्स हो जाएगा. वेक्टर है ये, स्टेट है, ऑपरेशन नहीं है. So I write, so the first qubit is ket 0. So what's the vector for this qubit? 1 0. The second qubit is in a superposition. So what's the vector for this? 1 over under root 2, 1 minus 1. And then I take the tensor product of these two vectors and I end up with this thing. This is my input quantum state. Alright, now I've already figured out what the matrix for this joint operation is on the 2 qubits. That matrix is this. The UC0 matrix then acts on the input quantum state, yielding an output quantum state. Right, okay, so which is the same thing as what we've done over here. Now there are different kinds of 2 qubit gates. This is an example of a control NOT gate. Do you get the gist of it? So in a genuine 2 qubit gate, there is some correlation between the 2 qubits. The state of one qubit changes dependent on the state of the other qubit. So both of the qubits play a role in what happens to a qubit. Other examples, for example, could be a controlled phase gate. A controlled phase gate is something that does a phase operation on the second qubit if the first qubit is in a state 1. That's a controlled phase gate. Could you write the matrix for this? So one possibility is, first of all, you would want to write down the truth table. So ket 0 0, nothing happens because the first qubit is in a state 0. Ket 0 1, nothing happens because the first qubit is in a state 1. And what does a phase gate do? A phase gate, if you just looked at the single qubit gate from our previous lecture, a phase gate does the following. Nothing happens to ket 0, and if I'm fed in with ket 1, a phase factor is added. So this gate now acts exclusively on the second qubit provided the first qubit is in a state ket 1. So nothing happens to the second qubit if the first qubit is in ket 0. So these are the first two terms of the truth table. If the first qubit is in ket 1 and the second qubit is in ket 0, still nothing happens because the phase only appends to the ket 1 state. So still nothing happens. So I'm left with 1 0. However, if my input were ket 1 crossed with ket 1, my output is going to be ket 1 with a phase factor. The phase factor is a scalar, so I can write it anywhere. So this is the truth table for a controlled phase gate. Got it? So I think it's now going to be peanuts if I ask you to write the matrix for this gate. Could you give it a shot, please? What's the matrix for a controlled phase gate? Diagonal पे सारे 1 होंगे. What about that phase factor? Sorry. So this is the first column vector which represents the output with the first input state, second input state, the output corresponding to it, third, fourth, and so on. This is the matrix for the controlled phase gate. Yes, please.
Could you explain why the second last one doesn't have that?
Because of this thing. Because this is how we define a phase gate. Nothing happens to ket 0. If the second qubit is in ket 0, nothing happens. Alright? So, controlled phase gate. What about a controlled, if my phase is pi, if my phase were pi, right, 180 degrees. So I would have a scenario of this kind. So what would the matrix look like? This is a controlled pi gate. So I just insert phi equals pi, which is equal to minus 1. 1, 1, 1, minus 1. Zeros everywhere else. Salman, I would like students to do a controlled Hadamard gate. So you can have a controlled Hadamard gate, which really means you apply a Hadamard gate onto the second qubit if the first qubit is in a state ket 1. Should be able to write down the matrix for this. Really, really easy stuff, by the way. Or I'm simplifying it too much for you, perhaps. Now, these are all the building blocks of quantum computers. If you would like to understand how quantum computers work, why they are so powerful, why they tout so much promise, why is there a gold rush for quantum computers, these are all the ingredients for building a quantum computer. By the way, there are some other gates as well which might become really important. For example, a Z gate, which has a matrix. So this is a single qubit gate which has a matrix 1, 0, minus 1. This one. And a Y gate, 0, minus iota, iota 0. This is a single qubit Y gate. All of these unitary operators, all of these matrices, by the way, represent unitary operators. If you look at any of these matrices, you will find that each one of them satisfies the property that the dagger of U equals the inverse of U, which means that all the gates are unitary. All right, there was a question somewhere. Yes, please.
So can you repeat what you just said regarding that inverse and unitary?
So this is how we define a unitary matrix. A unitary matrix is one for which the dagger of the matrix, which is the transpose of the complex conjugate, if that equals the inverse of that matrix, it means that we have a unitary gate. Yes, please.
So how does that become minus?
This thing? So if I just put pi here, ei pi is cos pi plus iota sin pi is minus 1. Yes, please? In the first qubit and 1 in the second qubit. Yes. All right. Now let's move on to our first quantum algorithm, and the only quantum algorithm that we're going to discuss. All right, there's a lot of commotion today. Please, some attention is needed. So why are quantum computers powerful? Any ideas? Why are they set to replace classical computers? Oh, at least that's what the promise is. Sorry? Faster computing. Why faster?
One qubit can hold more information.
Exactly, because 1 qubit really can hold a world of information in it. Not only can it be in a basis state, ket 0, ket 1, it could be in a superposition state and an infinite variety of superposition states. For example, let me give you an example. If I have the number 0, let's consider, say, 3 bits. 3 bits. Now with 3 bits, and I'm just talking about Boolean logic, I have 8 different kinds of sequences. I could have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Nothing quantum about this so far, it's just classical Boolean logic. I have 8 different kinds of sequences, 2 raised power 3 sequences for 3 bits. Each bit is a binary digit. It has 2 possibilities, 0 and 1s. Now suppose the task is to find out what happens when a function acts on a sequence x. Now all of these are sequences, all of these are x's, and there are 8 kinds of x's. I want to find out what happens when the function acts on a sequence, and the function has 2 outputs, 0 and 1. So it takes a 3-bit string and outputs a single bit. The single bit is 0 or 1. That's what the function does.
That's also why it's not reversible, right?
Yeah, it's not reversible. So the function x takes x, and which is a 3-bit string, and gives you 0 or 1. So it gives you either 0 or 1, and just one of these bits at a time. This is what the function does. Now if you want to find out what the function does on an x, you need to have a machine that does the f for you. It's a calculator that does the f for you, and it has 3 inputs. So it's fed in with the 3 inputs. The first bit, bit number 1, bit number 2, bit number 3. This is bit 1, bit 2, bit 3. You feed in the 3 bits. Each bit is 0 or 1. And then you get a single output, which is 0 or 1. So you initialize your machine, create 0, 0, 0, put it into the oracle or the machine, and it gives you an output. And you do it 8 times. And each time you have to prepare a different input. Each time you would prepare one of these strings, feed it into the machine, and note down the result 8 times. All right. Now, what I could do conceptually with a quantum computer is the following. Now, this is a classical machine, a classical computer. With a quantum computer, I can exploit superposition. So I can just have 3 qubits. Instead of 3 bits, I can feed in 3 qubits into this quantum computer, into this quantum machine. And those 3 qubits could be, so let's draw this quantum machine, hypothetical quantum machine. Now, since quantum mechanics deals with operators and unitary operators, I need to design some kind of unitary operator, some transformer U sub f, which takes in 3 qubits instead of 3 bits. So what I could do, the naive thing to do, is I take 3 qubits, each one of them is in the state ket 0. So my input is ket 0 crossed with ket 0 crossed with ket 0, and then somehow this oracle is designed, this machine is designed that I get an output. I somehow get an output f of 0, which now 0 is the decimal version of 0. So each of these strings has a decimal version. So this is 0, 1, 2, 3, 4, 5, 6, 7. So I can design my quantum computer such that my output is kind of encodes what the function does on this input state. But the good thing is, there's a good thing and a bad thing. The good thing about quantum physics is, now if you use this naive approach, there are two problems. The first problem is that the output is just a single bit. But that's all right, because your output is a single bit, 0 or 1. So if, for example, my input is 0, my output could be 0 or 1. If my input were 1, which means I feed in this input quantum register, this input quantum state, I can run my machine and get an output on this sequence, which is f of 1. I could then run this machine on another input, a third input, and my output is going to be f of 2, and so on. So the good thing is that this quantum machine works at least as good as the classical machine. You can feed in 8 different sequences of 3 qubits at a time, but it's not better than a classical machine. So you have to run this machine 8 times. But the great thing about quantum physics is that instead of feeding it in with each of these naive states, I can feed it in with a superposition of all the 8 states in one go, can't I? So instead of this simple nice input, I can create a more complicated input. And how do I do that? What do I need to input? I input cat 0, 0, 0 plus 0, 0, 1 plus 0, 1, 0 plus 0, 1, 1 plus cat 1, 0, 0 plus cat 1, 0, 1 plus cat 1, 1, 0 plus cat 1, 1, 1. And what do I do for normalization? Under root? Under root 8. So I can feed it in with a superposition, a giant superposition of 8 basis states in one go. In one go. And since quantum physics is linear, the function is going to act on each of these 8 basis states at the same time. All right. Now this is the key moment of truth. So in one go, if this operator acts on this giant input state, so this is a giant superposition state, in one run, so instead of 8 runs of the experiment, you just have 1 run of the experiment. If you had 4 qubits, instead of 16 runs, you could have 1 run. If you used 5 qubits, instead of 32 runs, you could have 1 run. If you have, say, 100 bits, instead of 2 raised to power 100 runs of the experiment, you could just do it in 1. This is exponential speed up. So this effect is called quantum parallelism. So you're looking at all the inputs in parallel because you have the ability to create superposition states. And in this case, if I would kind of try to achieve the entire quantum operation in one go, the function is going to act on each of the individual component states in one go. F of 7. So I'll get the output. Now I'll get a superposition at the output. So each of these is 0 or 1. So this could be 0 or 1. This could be 0 or 1, 0 or 1, because I just have 1 qubit at the output. And now that 1 qubit is in a superposition. So what's wrong with this? So I get something, I get quantum parallelism because I can feed in a giant input state which is in a superposition. So I can get exponential speed up. Or I could use exponentially less resources. Instead of n resources, I would need log n resources. I can exponential speed up. However, what's the problem with this? So quantum physics helps you because it creates superpositions, but quantum physics also defeats you in some way. So what is that defeat? What are we looking at in terms of defeat here? Exactly. Exactly. So even though this is a superposition of 8 outputs, 8 different states, you can't measure superpositions in one go. Because if you have a superposition and you will have different detectors at the output, only one of them is going to fire at one time. So all your entire nice, beautiful, pristine, serene, coherent superposition state, beautiful looking, is just going to collapse into one of the outputs. One of these will appear and all the others will disappear, and you wouldn't be able to tell which one of it is, because each one of them has the same probability. So even though you have superposition and parallelism and exponential speed up, you can't measure it. You can't see your outcomes properly in one go because of this collapse of the superposition. So what a quantum algorithm is designed to do, it is designed in a fashion so that you get advantages from superposition and parallelism, and then your output is designed in such a way that it tells you one of the possibilities. And I'm going to show this to you with an example. Before the break, I want to ask you one question. The question I would like to ask you is, with these 3 qubits, how can I create superposition, this giant superposition? What kind of logic gates, quantum gates do I need? Of all the gates that we've seen today and in our previous lecture, is there any kind of gate that you've come across that can create this superposition state from ket 0 cross ket 0 cross ket 0? Or
The control not gate.
control NOT gate. The control NOT gate doesn't do anything to the control qubit. So the control NOT gate, this qubit sometimes is called the control qubit, and this is sometimes called the target qubit. So nothing happens to the control qubit. So any idea what kind of gate you could use? Hadamard. On which qubit? All 3 qubits. If you have 3 wires coming in, ket 0, ket 0, ket 0, and you put a Hadamard here, beam splitter wala, if you're talking about photons, Hadamard gate here. This is your homework problem perhaps. You can kind of see that the overall output from this thing is going to be this particular state. So you can create this giant superposition. Alright, so let's take a 10-minute break and then we'll reconvene to discuss our algorithm. Let's get going with our algorithm. The algorithm that I'm going to present is one of the earliest examples of quantum algorithms. We've seen that the great advantage of quantum physics is that it can create superpositions. And when it can create superpositions, you can feed the big superposition state into your quantum computer and it can compute whatever it needs to compute in one go. But the problem is, how do we extort or extract information from this? Because we have this measurement problem that a big superposition is created. Niche baith jao, niche baith jao. A big superposition is created, but it collapses. You can't see the superposition. We've seen this in our interferometers. The interferometer is just ket 1, ket 0 at the output. Every superposition collapses, and the best you can get are probabilities. But you need certain answers. So how do we circumvent this problem? How do we bypass this problem? And that is the task of the designer of a quantum algorithm. So the algorithm that I'm going to describe is one of the earliest proposals for an algorithm, proposed by 1985 or so by an Oxford physicist, David Deutsch. Now this is not an incredibly useful algorithm, right, for practical purposes. It's a kind of a useless, fantastically useless algorithm. But the key point of me presenting this algorithm to you because is that it's number one, the simplest you can think of, and the second point is that it brings home the idea of quantum computing and why quantum computing is useful and how can we circumvent this measurement problem that I've just alluded to. Now let's start off with the Deutsch algorithm. Now what is the Deutsch algorithm? Every algorithm wants to solve some problem, and the problem that we would like to solve is we want to make a decision. अभी ध्यान से सुनो क्योंकि ये फिर मुश्किल हो जाएगा आपको. Now the algorithm is we would like to make a decision. We would like to resolve a certain property of a function and we want to decide whether that function is one of two kinds. Is f, the function, constant or balanced? Now what does it mean? I have some digit x which can be 0 or 1. This digit x can be 0 or 1 and a function acts on this and it gives me a digit y, and y can be 0 or 1. And there are two possible inputs. The domain of x, the domain of this function is the set 0 and 1. So it means that the function can act on 0 and it can act on 1 to give me 0 or 1, right? So the range of this function is also 0 or 1. And these are just single digits, single bits, 0, 1 or 0, 1 here, okay? Now there are two kinds of f's. One is called a constant f, the other is called a balanced f. How do we define this? So now I can draw a table to describe the two different kinds of f's. So if x is 0, if f of x were 0 and if x were 1, if f of x were still 0, so no matter what the input is, if the function always gives you 0, then it's called a constant function. This is one possibility. The other possibility for a constant function is that it gives 1 no matter what the input is. So these are two scenarios for a constant function. This is kind of scenario 1. This is scenario 2. And this is the constant function example. Okay? So there are two possibilities. One is that the function output is always 0, no matter what the input is. The other possibility is that the function output is always 1, no matter what the input is. This is an example of a function that we can call it to be constant. The other possibility is for a balanced function. Now the balanced function is defined as in the following fashion: 0 gives you 0 and 1 gives you 1, or the other way around, 0 gives you 1, 1 gives you 0. So if the input is 0, output is 0, and input 1 gives you 1, so the outputs are of both kinds, 0 and 1. So this is an example of a balanced function. So, and there are two scenarios for balanced function. This is scenario 3. This is scenario 4. All right, you got the kind of definition of our constant and balanced function. It's like a coin. If you have a coin, if it has head on both sides, it's constant, or it has tail on both sides, it's constant. But if it's a fair coin, it would have head on one side and tail on the other side. It doesn't matter which side, but there will be two alternate outputs. Okay, so this is the table for a constant function, and this is the table for a balanced function. Now, how would you solve this problem classically? You have a machine or a kind of classical computer or a calculator. First you input 0 and you find what the output is, f of 0. Alright, simple. But then you need to do another by changing the input, because this just one run of the experiment can't tell you whether the function is constant or balanced. So what you would need to do is you would take the same calculator and now initialize your input in a different fashion so that it's 1, and you find out what the output is. That will be the function acting on 1. Now you compare these two outputs. If the two outputs are the same, this scenario or this scenario, you declare that the function is constant. And if the outputs are different in each cases, you declare that the function is balanced. Got it? This is how you do this classically. Now these are, so you need to do two experiments. Now this looks very mundane and kind of unproductive to tell you that a quantum computer could do this in one go. That's why it's an incredibly simple algorithm. In fact, if you have a function that takes in 10 bits and is still a binary function at the output, you could also do this in one go with a quantum computer. But just to exemplify how the quantum computer works and how it exploits parallelism and superposition, I'm taking this really simple example. And when you take any course on quantum information processing, this is the first example that you will encounter. So I hope you have a good idea of what the problem statement is. Now the quantum algorithm means let's draw a quantum circuit, a quantum network that achieves this efficiently in one run, just in one run. In order to be able to do that, I need to define another 2-qubit gate. Right? Now, does everyone know what an XOR gate is? Alright, so I'm going to explain what an XOR gate is. XOR stands for exclusive OR. In normal computers, I think this is what the symbol looks like. I've forgotten, but I think this is it. So what an exclusive OR gate does is it has two inputs, one output. So let's draw the truth table for the exclusive OR gate A, B, X, or let's call it Y. If both inputs are 0, the output is 0. If both inputs are 1, the output is still 0. But if only one of the inputs is 1, the output would be 1. So it takes an exclusive OR of the two inputs. This is how we define an exclusive OR. An OR gate would also have 1 over here, but this is an exclusive OR. It gives you an output 1 only when either of the inputs is 1. Exclusive OR gate, and the symbol for this is this Y equals exclusive OR of A and B, and the symbol for this I think is A plus sign encircled. Okay, this is the kind of, this is how it is denoted. All right. Now we would like to define a quantum gate that implements an exclusive OR conditionally, a conditional exclusive OR gate. Ta-da. Does this look like an exclusive OR gate? Yes, it does. So the second qubit carries the result of an exclusive OR between the two input qubits. This truth table is very similar to this truth table. So the controlled NOT gate implements a kind of an exclusive OR operation. Just look at the similarities. Just ignore this first qubit here, because the first qubit, nothing happens to it anyway. It's like a scratch register. It's like a rough piece of paper. You scribble on it something and it doesn't matter what's on this piece of paper. So the second qubit, 0110, 0110, carries the result of an exclusive OR operation between these input qubits. So a control NOT gate is a kind of an exclusive OR gate. Now what we would like to do is we would like to design a quantum circuit that does the following. A controlled UF operation. And what the controlled UF operation does is we define it in the following fashion. If this input is ket X, this input is ket Y. Now this is our definition. All right. I'm going to define what a controlled UF gate does. A controlled UF gate does the following. If you feed in first qubit state X, second qubit state Y, nothing happens to the first qubit, like in any other controlled operation. But the second qubit may or may not change. And the output in the second qubit is Y, this Y, exclusive OR with function f acting on X. Got it? Now I give you 2 minutes just to think about this and if it makes sense. This is my definition. See if you understand all the nomenclature here. X and Y could be 0 or 1. Just forget about what the cases are. Is this something that you understand? Up पूछो. No, that's different. That's different. Yes, please.
So does the UF gate does the operation when the X is the qubit?
Sorry?
When X is like then the UF does the operation.
If Y is 0, this is 0 exclusive OR with f of x. So what this gate does, it does nothing to the first qubit, and the second qubit takes up a value. That value is the exclusive OR of this input value with the function f acting on the state of this qubit. Okay?
I was asking when does it get triggered? Like here was getting triggered when the input gate was 1.
So it depends upon what f of x is. So it's going to change. All right? It's slightly more complicated. So as a do-it-yourself problem, choose a particular f. A particular f would mean, where is my definition for the kind of f's? Where have I defined my f's? Can you? All right. Choose a particular f. This scenario, this scenario, this scenario, and work out the truth table. ठीक है? किसने सवाल पूछा था? ठीक है? Just choose one of these f's and work out the truth table. Now this is our definition for our logic gate. Yes, please.
So after the controlled F gate has acted on Y, will get X remain unmodified after?
Yes, ket x always remains unmodified. Okay, this is our control qubit, nothing happens to it, but it determines what happens to the second qubit. Yes, please.
If we let f of x equals to x, would that produce a control not gate?
Yes. It will produce a control NOT or exclusive OR gate. Yes, good point. All right, so now let's, with this definition, equipped with this definition of a controlled implementation of the function UF, let's build a quantum circuit. All right, the quantum circuit I would like to build is the following. All right. Now let's progress our quantum state through this circuit. Now what does the circuit look like? The circuit has two qubits, so two wires coming in, quantum wires coming in, could be photons, could be spins, we don't care at the moment. The first qubit is initialized in the state ket 0. The second qubit is initialized in the state ket 1. And we look at how the quantum state progresses successively as we go through this circuit. All right. First of all, let's see what happens over here. This is our input state. Let's call this psi 1. So psi 1 equals ket 0, first qubit. Can everyone see blue from the back? Blue nazar. So the first qubit ket 0 crossed tensor product with ket 1. Normalized, right? Okay, so far so good. This is our input state. Now time progresses from left to right. So we move along the quantum circuit, the quantum network. We reach here, right? Let's call the quantum state here psi 2. We're not measuring anything so far. So our psi 2, it's going to be different from the input state. How? What's going to happen? Is something going to happen to the second qubit? No. It's going to be remain ket 1. All right. अच्छा, एक चीज और करते हैं. Let's apply a Hadamard gate here as well. Okay, doesn't matter. So this state will also be transformed. Got it? So we have two Hadamard gates. One Hadamard gate on the first qubit, the second Hadamard gate on the second qubit. This is our state psi 2. All right. Now what we would like to do is the following. So just expand this. Just expand this. So psi 2 1/2 big brackets 0 0, or I could write for your convenience ket 0 minus ket 0 ket 1 plus cat 1 cat 0 minus cat 1 cat 1. All right, so this is the quantum state on this location. Yes, please, you have a question? Swal? Now the 2 qubit state. So far the 2 qubits are acting independently, the 2 gates are independent, but now you see a controlled operation which is somehow connecting the 2 qubits together. It's kind of a correlation that is seeping into the system. Now we would like to implement this logic gate here. All right, so let's see what the output is going to be at this stage. Psi 3. All right, so far so good. Let's see what psi 3 is going to look like. Psi 3 equals 1/2. Now we just need to kind of apply this rule over here that we've already defined. Okay, nothing happens to the first qubit. ये वैसे ही आ जाता है. For the second qubit, we take the exclusive OR of what exists in the second qubit 0 plus exclusive OR f of 0. It's just this definition over here. So how do we define this gate? We take the exclusive OR of what's in the second qubit y with the function f acting on the first qubit. The function f acting on the first qubit, which is 0, exclusive OR with what already exists in the second qubit, is just a mapping, an implementation of that gate onto this state. All right, minus nothing happens to the first qubit. Second qubit has a state 1, exclusive OR with the function f acting on the first qubit. All right, and then plus cat 1 0 exclusive OR function f acting on 1 minus 1 exclusive OR function f acting 1. Got it? So far so good. Any confusion out of this point? I'll give you 1 minute to think about it. Yes, please.
वो पहले डिफाइन किया था कि जब गेट 0 होगा तो फिर इस पे कुछ एक्ट नहीं करेगा अगर फर्स्ट वाले में.
किधर?
सर मुझे कंफ्यूजन कि अगर गेट 0 है तो फिर दूसरे वाले पे क्यों एक्ट किया?
नहीं यहाँ पे ये अगर फर्स्ट समझाने दोबारा बोलो.
अगर क्या पहले वाले में गेट 0 है
इधर नहीं, हमने ऐसे डिफाइन किया है. This is our definition for the controlled function, that this is how we define it. The second qubit takes up a value which is the exclusive OR of the input to the second qubit and the function acting on the first qubits. This is how we define it. Yes. Yes. Any questions for this? This thing? ये इसमें प्रॉब्लम है क्यों? So this is cat 0, this is cat 0. So cat 0 crossed with cat 0 is 0 0. All right, any questions for this psi 3? Yes, please. Yeah. So this is x, this is y, this is our y, this is x plus f of y, sorry, y plus, so this is my x. Excuse me, can you pay attention, otherwise we'll just get nowhere. This is my x, this is my cat y, cat x, cat y, my input. And what's my output? The first qubit remains cat x, right? It remains cat x. What happens to the second qubit? It's y exclusive OR with the function acting on x, right? So this is just an implementation of this. Yes, please.
So this means apart from that, get 0 will apart. 0 plus f of 0, this in itself is जो ऊपर लिखा हुआ है.
G. This is this thing. I think this is pretty simple. All right, so now let's simplify this a bit further. 1/2 get 0. Now if you look at the truth table for an exclusive OR operation, what is the result of an exclusive OR with 0? It's just the second thing, right? So an exclusive OR with 0 just returns the second object, f of 0, correct? How do you know this? If the first qubit or one qubit is 0, the output is just the second qubit. So this 0 carries over here, this 1 carries over here, right? So this is f of 0 minus ket 1, 1 exclusive OR f of 0 plus ket 1 f of 1 minus 1, 1 exclusive OR f of 1. All right, so far so good. Yes, please. Where? Yes, please. हमें देखना है ना, हमें कांस्टेंट और बैलेंस अभी यूज नहीं कर रहे, हमने देखना है कि फंक्शन कांस्टेंट है या बैलेंस्ड है. हमें भी अभी वी हैव नॉट इंसर्टेड एनी वैल्यू फॉर द फंक्शन एज येट, राइट? So this is independent of whether the function is constant or balanced. Let's move on. So now what we would like to do, you had a question? आपका question था? Can you speak up?
1 plus f of 0, why wouldn't that just be 1 according to the
Why? We don't know the value of f of 0. It could be 0 or 1. Which table?
the one about a, b and y?
So which row is applicable here?
It's the third one.
This is not 0, this is f of 0. Okay? Alright, now let's look at this function over here. Is anything, so now we're in a position, yes please.
So in the third term of these fractions, yes, shouldn't it be get 1 and get 0 for the intention order of get 1?
So the 0 exclusive OR with anything is that anything. Alright, now what we would like to do is the following.
So can you say that one exclusive OR with anything is the opposite of that anything?
I think this is pretty simple. Yes, please. F? We'll do that later. We'll do that in a minute. Alright, so this should be pretty clear to you. There's nothing hidden. Everything is in front of you over here. Now this term could be 0 or 1. Right? And this term could also be 0 or 1. And there's an f of 0 here. And there's an f of 0 here. For a minute, let's consider these two terms over here. If this term is 0, suppose f of 0 is 0. If this term were 0, what would this term be equal to? 1. If this term were 1, what would this term be equal to? 0. The first qubit is ket 0 in both of these terms. So nothing happens to the first qubit. But this, so if I were to factorize this, now let's look at this very carefully. 1/2 big brackets, first qubit ket 0, and I just want to factorize out ket 0 from this. So I can just bring out ket 0, tensor product f of 0 minus 1 exclusive OR with f of 0. Can I do that? Yes. So far so good. Likewise, this term would become plus ket 1 f of 1 minus 1 exclusive OR f of 1. Got it? Fine. So far so good. Just factorization. What should I erase? Let's erase this. No, I need all of this. I'm still at psi 3. If this term is 0, this term is 1. If this term is 1, this term would be 0. If this term is 0, this term would be 1. So these two terms are opposite to one another. So you get 0 minus 1 here or 1 minus 0. Here you would get 0 minus 1 or 1 minus 0. So what you would like to do is the first qubit, so 1/2, this is our big coefficient, ket 0 crossed with ket 0 minus 1. Now I need to take this term ket 0 minus 1, or it could be minus ket 0 plus 1. So all of this could be with the minus 1 factor. And what determines whether this is positive or negative? The value of f of 0. The value of f of 0 determines whether I put a minus sign here or I don't.
Sir, can you please explain how you replaced that entire term with ket 0 minus ket 1?
So there are two possibilities. This could be 0. If this is 0, this is 1. If this is 1, this is 0. So it's 0 minus 1 or 1 minus 0. So what I'm going to do is, this is 0 minus 1, but it also could be minus 1 times 0 minus 1 with a coefficient or a power f of 0 plus ket of 1 crossed with minus 1 raised to power f of 1 ket 0 minus 1. Is this making sense? Why not? यार कुछ सोच लो, ये अलजेब्रा है. Is this all making sense? No. You see, if f of 0, let's see if this is making sense. If f of 0 is 0, what's minus 1 raised to power 0? 1. So you left with 0 minus 1. So depending upon this value f of 0, if this were 0, you would get 0 minus 1. Ket 0 minus ket 1. And there's a positive sign here. So depending upon the value of f of 0, you either get ket 0 minus 1 or ket 1 minus 0. And these two terms are just related by with the minus sign. That minus sign, whether you apply it or not, is determined by f of 0. So now this is our psi 3, and what I could do is half. This is just a number, So I could bring this out, minus 1 f of 0, ket of 0 crossed with 0 minus 1, and I could convert this into half square root plus minus 1 f of 1 ket 0 minus ket 1 square root 2. Now let me finish this. Alright, so this is just algebra, nothing complicated. Now what I would like to do is the following. Yes, please. Now what I would like to do, yes please. मैंने इधर इसको break up कर दिया. Now what I would like to do is, any guess as at what would be my next step be? अभी और factor out नहीं होगा. The hint is that now I don't care about the second qubit, because if, alright, so let's factor this out at the very last step. So this is all kind of nice and easy. So let's factor it out here. Okay. So 1 over under root 2 minus 1 f of 0 ket of 0 plus minus 1 f of 1 ket of 1 tensored with, alright. Now what should I do? What should my next step be? I need to add another element in this circuit, another gate. Don't talk about beam splitter. This is a generic Hadamard gate where which qubit? First or second? So I put a Hadamard gate here. And if I were to put a Hadamard gate here, I would generate a new state psi 4. Let's see what that state is going to look like. Psi 4 is going to be 1 over under root 2 minus 1 f of 0 ket 0 plus 1 over under root 2 plus minus 1 f of 1 ket 0 minus 1 over under root 2. All of this tensored with the second qubit. Alright. Now comes the final moment of glory. What I would like you to do now is factorize out the first qubit. Put ket 0 together and all its coefficients with it. Keep ket 1 together and all of its coefficients with it. Ignore the second qubit. We're going to do nothing with the second qubit. So psi 4 is going to look like the following. 1 over under root 2 ket 0. The coefficient of ket 0 is minus 1 raised to power f of 0 and minus 1 raised to power f of 1. Minus 1 f of 0 plus minus 1 f of 1 plus, with ket 1 we have minus 1 f of 0 minus 1 f of 1. So this is our first qubit and our second qubit remains unchanged. I don't care about the second qubit now. Now, is it possible to measure just the first qubit and tell what kind of function we have? So if I look at this, if I look at the top qubit over here, this top qubit is coming out after the Hadamard gate. So we have a Hadamard gate, then we have a controlled application of UF and Hadamard gate here as well, and then another Hadamard gate here, and now this wire carries this qubit over here. If I were to put a kind of beam splitter here, PHV or P01, which splits out ket 0 or ket 1, and if I can tell whether the function is constant or balanced depending upon which detector clicks, is that possible? Yes. If the function is constant, which of these terms is going to survive? if the function is constant, this thing f of x has equal values for both the inputs. So f of 0 is the same as f of 1, f of 0 is the same as f of 1. So if the function is constant, which of these terms is going to cancel out and which of these terms is going to survive? So this is going to cancel out. So if my function is constant, my output on the first qubit is going to be ket 0. This term is going to survive. So ket 0 means if this detector clicks, the function is constant. If, however, the function is balanced, which is scenario 3 or scenario 4 here, f of x has different values for 0 and 1. F of 0 is the opposite of f of 1. See, 0, 1, 1, 0. In that case, since there's a minus sign here, this term is going to survive and this term is going to cancel out, because this is positive, this is say plus 1, this is minus 1, or minus 1 and plus 1. This term is going to be washed away and only ket 1 is going to survive. So with certainty, this detector is going to click. So this detector clicking shows that f is balanced. Hence, in one go, in one shot, by creating this superposition through these Hadamard gates and a clever application of a controlled function and a Hadamard gate at the end, we have mapped the problem, encoded the problem of deciding whether the function is constant or balanced into two orthogonal outputs, two mutually exclusive outputs. One output is obtained, the function is constant, and the mutually exclusive output is obtained, the function is balanced. See you on Tuesday.